All right, let's jump into wave optics. It's amazing how light just bends and interacts to create those dazzling effects we see every day,
Yeah.
like a straw looking broken in a glass of water,
Uh-huh.
or those vibrant colors in a soap bubble.
Right.
We've got some pretty cool research and notes here to help us really understand the science behind these visual marvels.
What's really cool is that these effects happen because light acts like a wave.
Oh, okay.
Once you get interference and diffraction, you'll see things in a whole new light, literally.
So, to kick things off,
Mm-hmm.
let's talk about Young's double slit experiment. I mean, it sounds simple enough,
It is, yeah.
but it totally changed the way we think about light.
Yeah. See, people used to think light was just particles, like little bullets.
Okay.
But Young's experiment proved them wrong. Imagine shining a light onto a barrier with two tiny slits.
Okay, got it.
If light were just particles, you'd just see two bright lines on a screen behind it, right?
Makes sense, like two beams of light passing through.
Exactly. But Young saw multiple bright and dark bands instead. Interference fringes.
Wow.
It blew everyone's minds because it showed that light behaves like a wave, spreading out from those slits and interfering with itself.
So those bright bands, that's where the waves, like, amplify each other?
Yes.
And the dark bands are where they cancel out.
Yeah, it's like a cosmic tug of war.
That's a cool way to picture it.
Yeah.
So this distance between the fringes, the fringe width, that tells us something about the light.
Absolutely. Take a CB, for example.
Got it.
You know those shimmering rainbow colors?
Yeah.
That's interference in action. Those closely spaced tracks act like tiny slits.
So that's how that happens.
Yes. The light waves reflect and interfere, creating those vibrant colors.
Right, the closer the tracks, the smaller the fringe width, and the more, like, intense the color.
Exactly.
I'm starting to see everyday objects in a new light, literally.
Mm.
But there's got to be more to this interference pattern than just bright and dark bands, right?
Oh, definitely. The central fringe, the one right in the middle, is the brightest. The light waves there travel the same distance from both slits, so they're perfectly in sync, reinforcing each other.
And as we move away from the center,
The intensity fades
why is that?
because the waves get more out of sync. Think of it like a symphony. The central fringe is the crescendo, and the intensity decreases as the waves, get out of step.
I like that analogy.
Yeah.
So what if we shine white light, which is a mix of colors, through those slits? Would the interference pattern be white?
The central fringe would be white, yes,
Rough.
but as you move outward, it's a rainbow explosion.
Around.
Each color creates its own set of fringes because each color has a different wavelength. It's like a prism splitting white light, but through interference.
That's incredible. So those shimmering colors on a soap bubble, that's different wavelengths interfering.
Exactly. It's nature's light show.
Okay, this has been amazing. Does the environment, like where this is happening, affect the pattern? Like, would it look different underwater?
You're on the right track. The medium definitely matters. Water, air, glass, they all have different refractive indices, meaning light travels at different speeds through them.
Oh, so that affects the wavelength too.
Yes. And since wavelength affects the fringe width, the pattern would definitely look different.
So if we did Young's experiment underwater, the fringes would be closer together because the wavelength gets smaller.
Precisely. Higher refractive index means shorter wavelength, smaller fringe width.
It's like the whole world is playing with light to make these patterns.
Absolutely. And we've only just begun, ready to see how this works in practice with a real problem.
Let's do it. I love a good challenge.
Welcome back. I hope you're ready for more wave optics fun.
I am. I'm still amazed by how much we can learn from just those bright and dark bands.
It's fascinating stuff, right?
Absolutely. So where do we go from here?
Well, we've talked about how the intensity of light changes within these interference patterns.
You mean like how the central fringe is the brightest and then it kind of fades out?
Exactly. There's some really cool math that explains why.
Math. I know. Just kidding.
I know, right? But it's pretty straightforward, actually. The intensity at any point in the pattern depends on how much the waves are either amplifying or canceling each other out.
Okay, I'm following so far.
Good. So imagine two waves meeting. If their peaks line up perfectly, they add up and you get maximum brightness.
Oh, I see.
But if a peak meets a trough, they cancel each other out, and that's darkness.
So it's all about how the waves are interacting at each point.
Yes, and this, believe it or not, has tons of practical applications.
Really? Like what?
Well, scientists use these principles to build incredibly precise instruments.
Oh, wow.
Instruments that can measure tiny distances or even detect super subtle changes on surfaces.
So all because we can measure those tiny changes in brightness.
Exactly. It's like reading the whispers of light.
That's poetic.
Now, how about we shift gears a little? Let's talk about how the environment affects these interference patterns.
Okay, we talked a little about how light slows down in water.
Right, and we saw how that leads to smaller fringe widths, remember? But let's put this into practice. I've got a real-world challenge for you. Imagine our classic double-slit experiment, but this time it's submerged in a tank of water,
Okay, I can picture that.
and we're using a red laser pointer for our light source. What do you think would happen to the interference pattern compared to when it was in air?
Okay, let me think. Water has a higher refractive index than air, right?
Yes.
So the light slows down, the wavelength decreases, and the fringe width also gets smaller.
Spot on. It's like the water compresses those light waves, making them dance in a smaller space.
Cool. And this change in fringe width, it's related to the refractive index, right?
Exactly. You're getting it.
So we could calculate the new fringe width underwater if we know the fringe width in air and the refractive index of water.
Exactly. It's all connected. Now let's get even trickier. What if we add a thin glass plate in front of one of the slits?
That's interesting. Glass also has a higher refractive index than air, so we'd slow down the light even more, right?
Yes. But it also does something else. It introduces an additional path difference.
Path difference.
The light passing through the glass has to travel a longer distance.
Oh, like it's taking a detour.
Exactly, and that shifts the whole interference pattern.
Really? The whole thing?
The central fringe, for example, wouldn't be at the center anymore.
Wow. So how much does it shift by?
Well, that depends on the thickness of the glass plate, its refractive index, and the wavelength of the light.
It's like a delicate balancing act.
Absolutely.
Yeah.
And this is just one example of how these seemingly small changes can have such a big impact.
It's incredible to think about all the cool experiments scientists can do with light. They're like choreographing those waves.
You got it. And speaking of choreographing light, we haven't talked about diffraction yet.
Oh yeah, diffraction is when light bends around obstacles. Right.
That's one way to think about it.
Okay.
But here's the crazy part. You don't even need two slits to see diffraction. You can get an interference pattern with just one.
What? How does that work?
Well, think of light passing through a single narrow slit. Instead of one wave, imagine it as a bunch of tiny wavelets.
Tiny wavelets.
Yeah, and they're all spreading out from the wavefront. As they spread, they interfere with each other. And you guessed it, you get a diffraction pattern.
So like each part of the wavefront is acting like its own little light source.
Exactly. It's like a mini light show within a light show.
That's a great way to put it. And the narrower the slit, the more spread out the diffraction pattern becomes.
That's right. It's almost as if the light wants to break free.
I'm starting to see that wave optics is really all about these interactions and how they create the world we see.
It is. And these interactions are super important for technology and our understanding of the universe.
Can't wait to learn more. We're back for the final part of our deep dive. I can't believe how much we've covered about light's wave-like behavior.
Yeah, it's been a wild ride. From interference and diffraction to seeing what happens when we throw in things like glass plates and changing the medium.
Right. It makes you wonder what else is out there, waiting to be discovered.
Absolutely. Sometimes we have to push the boundaries a bit, see how different things work together.
I like where this is going.
Let's combine some things we've learned. What if we have a glass plate AND, we submerge everything in water?
Whoa, double the trouble.
Exactly. Imagine our double slit setup. Underwater this time, with a green laser and, of course, a glass plate in front of one of the slits. Let's say we want to find out where those bright fringes will show up.
Okay, so we've got the water slowing down the light and changing its wavelength.
Yep.
And the glass plate adding that extra path difference.
Right. So how do we figure out where those bright fringes, the maxima, will end up?
That's a good question. It seems pretty complicated.
It is, but at its heart, it's still about constructive interference. Those bright fringes happen when the waves from both slits arrive at the screen in sync, amplifying each other.
So we need to look at the total path difference from the water, the glass, and the whole setup.
You got it. That total path difference has to be a whole multiple of the wavelength, but the wavelength in water, of course.
So many things to keep track of.
It's a delicate dance, finding those points where everything lines up perfectly.
A delicate dance, I like that. This deep dive has been amazing. We've gone from simple, everyday wonders
Yeah.
to understanding some pretty complex stuff about the nature of light itself.
And that's what it's all about, inspiring that curiosity and appreciation for the world around us. Wave optics shows us just how beautiful and complex the universe really is. There's always more to discover, more to understand.
Absolutely. Well, to all our listeners out there, we hope you've enjoyed this deep dive into wave optics as much as we have. Keep your minds curious, your eyes open, and never stop exploring the magic of light.